Good morning, good afternoon, and good evening, everyone, depending on the time zone. This is the talk, Large-Scale Data Validation with Fugue by Wang. Han is the tech lead at Lyft's machine learning platform, focusing on distributed computing solutions. He's the founder of the Fugue project, aiming at democratizing distributed computing and machine learning. Please take it away.
Hello, everyone. My name is Han, and today I'm going to talk about the scalable data validation with Fugue. And I will go through a demo first, and then just to wrap up. So let's directly go to the demo for now. So in this demo, assume that we have a very large collection of color balls, and we have data frames recording their colors and weights. And in this demo, we're going to do some validations on these data frames, either locally or distributedly. Let's start. First of all, let's read the data from the disk and also take a look at the sample data. So as you can see, this sample data is a data frame. It contains 8,000 rows. So actually there are 8,000 balls. It contains two columns, the color and the weight. And if we draw the histogram of the weight distribution by different colors, you will see that each color, they have their own distribution. And it seems they are normal distributions, but we're not sure. So we will find out through the demo. And also, let's take a look at the data we want to validate on. So this has 8 million rows, the original data set. And also here we have a dictionary called ranges. And this is the ranges of weight that someone provided to me. And they asked me to make sure that for different colors, the weight must be in these ranges. So this will be another validation task in this demo. Now let's start. The first scenario is we want to validate for each value in this data frame is within a certain range. And now let me introduce Pandera. So Pandera is so far one of the most lightweight Python data validation frameworks. So here we will use Pandera to do the validation. As you can see, with Pandera, we can write very simple code snippets in order to enable the validation. And in order to use Pandera, you have to define the data frame schema. And in this data frame schema, we say that we want to validate weight, and the column must be in float type. And also the value must be in the range of between 10 and 500. So this is a very intuitive expression of a validation logic. And we also have another data frame schema we call the bad rule, because here we assert that it's between 100 and 500. And we know that in this sample data frame, there are some values that is lower than 100. So we expect when we use this rule to validate this, the data frame, it should fail. So now, first of all, let's use the good rule to validate the sample data. And you can see it will just return original data frame. And now let's use this to validate. And as you can see, if we are using a bad rule to validate the sample, or we use a good rule to validate the bad data, we should get the schema error. Okay, so now let me introduce Fugue. So Fugue is also a lightweight package, Python package. It can quickly turn your native Python functions into something that can run distributedly on top of Spark, Dask, or any execution engine that Fugue supports. And in this talk, I'm going to use this transform function from Fugue to demo how Fugue can help on data validation. And we just import this transform from Fugue. And then we just rewrite this validation function. So instead of saying rule.validate sample, just say transform And here we provide the data frame, and here we provide the function. And also this parameter means we want the output to have the same schema as the input. So let's run this. Actually, this is just a rewrite of rule.validate sample, right? So it should have the same behavior as before. And let's also test this on the other rule. So as expected, we will see this schema error. But the true value of the transform function is that now this data frame no longer needs to be a pandas data frame. Now it can be a Dask data frame, it can be a Spark data frame, and it can be any data frame that Fugue supports. And also you can specify the execution engine to tell the system where to run this validation. So our distributed computing frameworks, if we use a distributed computing framework as our backend for transform, so this is what will happen. This is the original data frame, and it will be split to small partitions based on the default behavior of that computing framework. And then for each partition, we will run this validate to validate just this partition. And if everything is fine, we will just return the original data frame. So now let's take a look at an example. How can we change this sample, the pandas data frame, to something that is scalable? So now let's use Dask as an example. So this is a standard way for Dask to read data from a file system. And now this is a Dask data frame. And now to apply this validate on a Dask data frame, you just need to change this data frame to this Dask data frame. And also you can specify the backend to be Dask. So this transform will execute on the Dask cluster. And because we set the backend engine to be Dask, the output will be a native Dask data frame. So we can call compute to get the result. So if you want the whole thing to run on Spark, you just change this to Spark data frame and set the engine to a Spark session. And you don't have to change this, this validate function. And we just make this function to run distributedly with different execution engines. Okay, now let's take a look at another example. So now we have a hypothesis that for different color group, the weights are always normally distributed. So in order to do that, first of all, let's take a look at the Panda's native expression for this logic. And by the way, the Pandera, this is considered as an advanced use case for Pandera. So if you cannot follow 100%, it is totally fine because Pandera has very good documentation. And I will also share this Kaggle notebook after this talk. So look at this function. This function depends on the color value. And inside this function, we just return a different check of Pandera called hypothesis. So we want to do hypothesis testing, then we are using normal test from SciPy, and as well as the thresholds. But these two are very tricky. So because we want to validate the distribution by each color, so we just need to specify the group by color and to specify the value here in the samples. With this function, what we have to do is we have to go through the unique colors from sample. And for each color, we need to create a check. And in this sample, actually, we have 8 colors. So this contains 8 elements. And we put these checks in this weight validation. And then this is the logic for the original Pandera expression. So the real problem for this is not only, it's a little bit tedious, but think about that. If we have 8 colors, probably it's fine. But what if we have 8,000 or 80,000 colors, 80,000 partitions, then these checks will be a huge array. So this idea cannot scale very well on a distributed system or on very large data set. And also here with this rule, right? And we just validate on the entire data set. It took 15.7 seconds to finish the validation. Now let's take a look how Fugue can help in this case. So in Fugue, remember we use transform function. Actually, in transform function, if you provide a partition parameter, then Fugue will take care of the logical partition for the data set, no matter where the data is, on Spark or on Dask or on Pandas. And after the logical partition, each data frame or each small partition will contain only one color. And then with this data frame, we can perform the validation. So this will significantly simplify the task for validation framework because Fugue level takes care of the partitioning, and then the validation work, the validation framework, they only need to focus on with the same logical partition or with the same color of data frame, how can I perform the validation? So as you can see, no surprise, the code will become much, much simpler than before. So here we just define hypothesis testing as before, but we no longer need to have the group by and the samples, those two tricky parameters. It's straightforward. And also in this data frame schema, we only set one check instead of many checks, because this will operate on just the one partition of data that contains only one color. And with this idea, you can take a look how long it takes to operate on the exactly same data set. 8.2 seconds. Compared to this, it's almost 2 times faster. And it is also simpler and more intuitive. Okay, so now let's bring this to Dask. How can I run this partition and validate logic on Dask? So actually, it's very straightforward. We just change this data frame to a Dask data frame where we directly load from file. And then we just specify the backend to be Dask. And as you can see, even on the same Kaggle notebook, Kaggle machine, and even this process is reading from file, it is still faster than the Pandas version. So this is the power of a distributed computing system. If you have a very powerful computing cluster, it can process huge amount of data within very reasonable time. Okay, the next scenario is actually an addition to the existing scenario, to the previous scenario. So besides validating the distributions by color, we also want to validate the ranges for each color. So remember that we have this variable, we have this dictionary specifying the range for different color. How can we apply this dictionary to the entire data set? So again, here is the native Pandera solution. As you can see, this is normal check, it's the previous code, but this is new. This is to validate the range by different colors. And what we have to do is we have to treat the input data frame as a key value pair, so as a dictionary. So in the dictionary, the key will be the colors and the value will be the subdata frames belonging to that color. And we have to go through every key value pair of that groups. And for each group, we have to make sure the min and the max are within the given range, right? And not only this, we also have to add this additional check to the collection of normal checks. So we get one more check in the checklist, and the other things will stay the same. And also, by the way, if you have group by, no matter here or here, you have to have a dummy color validation inside the Pandera data frame schema. Right. So now let's take a look how long it takes on the entire data set. It was 15 some seconds, and now it's 16.6 seconds. Now let's take a look with Fugue how we solve this problem. Just like before, With Fugue, it takes care of the partitioning. So the Pandera level check will only face one color data frame. So the problem becomes much simpler. Here, the only thing we added is just one line of code. And this is a cross-column validation, where this data frame is already partitioned by color. And so we just need to make sure that the weight is between the ranges that is determined by the color column value of this subdata frame. Again, it is simpler, and also it is much faster than the previous solution. Now let's run it distributedly using Dask and see how long it takes. So again, if you want to run everything on Spark, just change this to a Spark session you initialized by yourself. And this data frame can be a pandas data frame, or it can be a Spark data frame. And as you can see, using Dask, it is still faster than the pandas solution, even on the same machine. In the last scenario, I just want to talk about something different. So in scenario 3, we still have the ranges to use, right? And in the last scenario, we no longer have this dictionary. We want to profile the sample data set and figure out this dictionary. And in this section, I'm going to show how Fugue can integrate with great expectations. And first of all, let's take a look at the great expectations code. One thing I really like about great expectation is they have a feature called mostly. Let's take a look at the example. So if you want to apply the range validation on a certain column, first of all, you convert this data frame into a great expectation data frame. And then you can just directly apply your validation. I want to assert that the weight column is between 70 and 500. This is a bad number because I know there are weights that's under 70. So this should fail. This should give me a false. But with this mostly of 0.8, I think this will succeed because I know that most of the data in sample, they are greater than 70. So mostly make it not 100%, but almost. So as you can see, this is false and this is true. This mostly is very, very useful if you want to fully automate your profiling and validation pipeline, because you profile on the existing data. And for the new unseen data, it is very common to see outliers. Although it's very small percentage, it makes the validation can't be 100. So you must set the mostly to a number that is close to 1, but not 1. Okay, with this in mind, let's see how we can write a simple validation function that can perform the validation on, if the data frame is already partitioned into a single color. Okay, so this is the function. We take several parameters. The first parameter is the min max belonging to that color. And the second is a sub-pandas data frame belonging to that color. And third is the mostly parameter. And what we do is we just convert this data frame to the great expectation data frame, and then we perform the validation. And here we just get the min and the max from the first parameter. And also we provide the mostly. And only if this result is not successful, we return the color value and fail the result as string. So look at this function. It is just a Python function, nothing special. It has nothing to do with Fugue, has nothing to do with Spark or Dask. So we can just do some unit test on it. Let's use the red color as an example. Assume that the min is 70 and max is 200. Again, we know that 700, for 70, most of the data will be more than 70, but there are some that is under 70. So if mostly is 0.8, then the process will succeed. It will yield nothing. we should get an empty array here. But if mostly is 1, then we should get something. We should get the red color plus a result. Let's see if this is the case. So this is the case. So if you provide mostly, and then it is empty, otherwise contains something. Okay, with this simple validate function, now we want to see how we can leverage Fugue to do the auto profiling plus distributed validation. So look at this function. This is also an advanced use case for Fugue. So you need to initialize the Fugue workflow. So Fugue is all about directed acyclic graphs. And here, just use that Fugue workflow directly. And the first step, we just need to bring the data frame into the workflow. And then we want to select color and min and max of weight. So actually, this is a group by color and to get min and max of weight. This constructs the ranges that we found in the previous sections, but it's in the data frame format, so it's fully scalable, no matter how many partitions, how many colors you have. And on the second step, we will just zip the ranges and this data together because they have the common column called color. So they will zip together by the color. And after you zip together and say transform by validate, so it will zip partition by color, and for each partition, you will apply this function. So this min max and this subset, they will belong to each color. And also here is how we provide the mostly parameter. And in the end, we should get a list of error reports, right? How can we deal with that error reports? In the summarize function, if the error reports is a list of errors, then we should assert that there is no error. But if there is any error, we will just throw an assertion exception where the message will be the first 3 error reports. So for this part, it will run with the given engine that you specified. And if there is no problem, this will finish silently. Otherwise, it will throw an exception. If this finishes silently, then we can just return the original data set. So this is the solution that can help you to do scalable distributed profiling and validation by different partitions. As you can see, if we test, if we profile on sample and then apply back on sample, we can set the mostly to 1.0. There is no issue at all. But if we set the data and then we still expect it to finish 100%, it will fail. And if we relax the mostly to 0.8, it will pass. And in the end, we just bring this to a distributed environment by providing a Dask data frame here and the engine, the backend here. So actually, as you can see in this function, we mixed the data frames. So for Fugue, we can take any type of data frames and we can also mix them. So for example, this can be a Spark data frame, this can be a Dask data frame. And where to run really depends on the engine. So now this function is fully scalable and it can operate on a very big data set. Okay, to wrap up, Great Expectations is feature rich and Pandera is straightforward. They both have very good support for pandas data frames, but both of them lack intuitive and scalable interface to do per group validations. And Fugue can help in this scenario because it can help, it can make Great Expectations and Pandera to focus on the single logical partition and pandas-based validations. And Fugue can take care of the rest. For example, various data sources, various computing engines, partitioning, and computing orchestration. In general, Fugue can make the validations much simpler and much faster. But of course, it has to integrate with Great Expectations and Pandaras to achieve this. So Fugue is open source. You can just pip install Fugue SQL, and you can also visit our website. And the Kaggle notebook I talk about today is here, it's public. And if you want to chat with our team, just go to select.fugue.ai. Thank you.